Welcome, everyone. On behalf of Forge College, I am so incredibly pumped to guide you through another explainer. Today, we're unrolling our engineering schematics, smoothing out the blueprints, really, and getting into the absolute architectural meat of transitioning from the EVM to the SVM. Specifically, we're tackling one fundamental, game-changing topic: why Solana uses reusable programs. Look, if you really want to build efficiently on Solana, you have to genuinely understand the philosophy behind its architecture. In our previous lesson, we spent a good chunk of time on transfer mechanics, comparing how different models behave. And naturally, that leads us right to the billion-dollar question that's probably floating around in your head right now. Why not just bundle code and data together like Ethereum does? In the Ethereum virtual machine, your smart contract is basically this self-contained box. The logic dictating how the token works, and the ledger of who actually owns what, they live inside the exact same house. But Solana completely shatters that model. It deliberately, strictly separates logic from state. But why go through all that trouble? Well, let's unpack it. Okay, to help you map out your mental architecture today, here's our roadmap. We've got 5 distinct sections. 1, the paradigm shift. 2, the engine at work. 3, the assembly line. 4, a quick code exercise. And 5, trade-offs and conclusion. All right, let's not waste any time. Let's jump right into the foundation. Section 1. The paradigm shift, separating code from state. So we really need to dive into the core philosophy of Solana's architecture and how it completely flips the Ethereum model you might be used to. Honestly, this is where you kind of have to rewire your brain a bit. Look over at the EVM model on the left. Every single time a new meme coin launches, developers are out there paying massive gas fees to deploy the exact same standard ERC20 contract logic for the 1,000th time. It's literally like building a brand new, highly secure bank vault from scratch just to store a different currency. It's madness, right? Now, over on the right, we have the SVM, Solana's architecture. Here, we have the strict separation. Immutable programs over here, mutable accounts over there. Programs are just executable binaries. They just hold the rules. Accounts are where the actual data and balances live. So Solana uses this incredibly efficient, reusable separation where one perfectly built bank vault handles the logic for everyone's different accounts. Section 2. The engine at work, orchestrating the single program. So if your custom programs don't actually own the data or the token balances, how in the world do they talk to each other to get things done on chain? Well, that brings us to a massive fundamental concept, cross-program invocation, or CPI. This is absolutely critical vocabulary if you're an EVM dev moving into the Solana space. A CPI is just a mechanism where one program calls another. It passes along account information and authorizes actions entirely without holding the token state itself. The crucial takeaway here is that your program isn't mutating balances. Instead, it's basically picking up the phone, calling the authoritative SPL token program and saying, "Hey, I've got the right signatures here, please move these tokens for me." And this anchor code snippet brilliantly illustrates how this actually looks under the hood. Let's break down the steps. First, context setup. Your program explicitly declares the accounts it expects: the sender, the receiver, the authority. Second, you gather CPI accounts and the program handle. You're explicitly referencing the SPL token program's deployed binary. Third, you execute the token transfer. Honestly, think of your custom program here as a bossy middle manager. It's an orchestrator. It securely borrows the SPL token program, delegates all the heavy lifting of enforcing rules and moving balances, and then just reports back that the job is done. I want this concept to be crystal clear, which is why it's literally the only thing on the screen right now. Your program is an orchestrator. It holds 0 token balances. I really cannot emphasize this enough. On Solana, your custom program just passes the account infos to the authoritative token program. You do not own the on-chain code that enforces token rules. You compose with it, you orchestrate it, you tell it what to do. Assuming, of course, you have the cryptographic signatures to prove you're actually allowed to. Section 3. The assembly line. End-to-end workflow. Let's take what we just learned about orchestrators and CPIs and map out an end-to-end workflow just so you can visualize exactly who signs a transaction and which account owns what piece of data. Check out this matrix of actors, accounts, and responsibilities. Let's walk through it together. The sender token account and the recipient associated token account, or ATA, are both actually owned by the SPL token program. It's the SPL token program's responsibility to hold those balances and enforce the transfer rules. Now, the payer is owned by the system, which is usually a user's wallet, and their job is simply to pay the network fees. Then we've got your orchestrator, which is a deployed program account responsible for coordinating the CPIs. And finally, the SPL token program itself, another deployed program account containing the authoritative logic. Notice how the SPL token program is basically the undisputed king of the token data here. It owns the accounts holding the balances, and it owns the logic. Let's see how this all builds into an actual transaction flow. First up, the client side assembles all the necessary accounts. It has to know exactly which accounts are going to be touched. Next, we might have an optional ATA creation. If the person receiving the tokens doesn't have a specific account to hold them yet, one just gets created on the fly. Then, your orchestrator performs that CPI we talked about. Finally, the Solana runtime executes all of these instructions atomically. That word right there is key, atomically. It means that if any single piece of this workflow fails, maybe a user didn't have enough tokens, or a signature was totally invalid, the entire transaction reverts. Everything cancels out and absolutely zero balances change. It is completely all or nothing. Section 4. Code exercise. Blueprint specifications. Time to roll our sleeves up and put this into practice. If you are writing the code for an orchestrator that wanted to do a checked transfer, here are your to-dos. First, you've got to read the amount field from the sender's account data. Second, check that their balance is greater than or equal to the amount they're trying to send. Third, if that passes, perform the CPI to the SPL token program. Fourth, and this is incredibly important, guys, refetch the two account data. And fifth, emit a balance log. So why is this exercise so vital? It's to reinforce that you must read and validate state before a CPI to avoid wasting compute if it's just going to fail anyway. And you absolutely must refetch the state afterward if you want reliable values. Why? Because your program doesn't own the data. Another program just mutated it. If you don't reload it, your program is literally looking at stale data. Section 5. Tradeoffs and conclusion. Now, any good engineer knows there is no such thing as a perfect architecture, right? So let's look at the dichotomy of this design choice. On the left, we've got the immense benefits. This model gives you predictable costs. It means standard tooling, like block explorers and wallets like Phantom. They just work straight out of the box because every single token uses the same interface. And of course, absolutely no duplicated logic bloating up the blockchain. But look at the trade-offs on the right. Centralized authority. If the SPL token program has a bug, every token on the network has a bug. This creates massive governance concerns. Any upgrade to that shared program requires intense, meticulous planning and strict backward compatibility because it's going to affect all token holders simultaneously. I really want to highlight this quote directly from the architecture docs. Reuse improves maintainability and UX, but centralizes upgrade and authority concerns. This elegantly summarizes the ultimate trade-off of Solana's single program, many accounts model. You're basically trading deployment fragmentation for centralized operational gravity. It's a fantastic trade-off for user experience and network speed, but it demands a very, very mature approach to security and governance from the entire ecosystem. So, I'm going to leave you with this final, somewhat provocative thought as you design your own applications. If your custom orchestrator program is totally immutable, how will you handle the SPL token program evolving in the future? It's a real puzzle, and it forces you to think deeply about your architecture and backward compatibility. Thank you so much for joining me on this explainer. To continue your Web3 journey, tackle some more exercises, and dive even deeper into Solana's architecture, head over and visit us at forge.college. Keep building, stay curious, and I'll see you next time.